Thank you, Dennis, to be part of this new Java Dev Day, now JConf Mexico. Thanks so much to be part of this, Dennis. And well, for the people that is following this channel, the best practices channel, well, Dennis, today we'll talk about a very interesting talk regarding the Northern Lights. As I remember, you are from.
I'm from Ukraine.
Yeah, and well, Dennis is principal member Oracle, and yeah, well, the scene is you. Thank you so much, and let's gonna start.
Okay, I guess you see my slides and you hear me pretty clearly, and you obviously see me. So first of all, I'd like to say thank you to people who stand behind the JConf Mexico, who committed themselves to make this event happening, especially in these uncertain times. As you may notice, like lots of conferences have been canceled, and still we're here together in JConf Mexico, and not just to promote ourselves and things that we would speak about, but to stand for the Java community globally, because we're from different locations and we just gathered to speak about Java and things we can do with that. So let me first introduce myself. My name is Dennis McCogan. I'm a principal member of technical staff and a member of Java Platform Group. This is a group that is responsible for Java development at Oracle. So with some of you, we have met in person around the world at DevOps conferences, JFocus, and maybe at some Java user group meetups in the US or in Europe. So as many of you, I write software for a living, but on my spare time, I do landscape photography for fun. Even though I call it fun and a hobby, people on the internet call me like a pro landscape photographer, and probably they are right, because one of my photos won a very prestige award as the best drone photo of 2019. Probably that's why, but I didn't consider myself as a pro, just a good one, a bit above the average. So what's this all about? We're here to listen a quite interesting story how my both skill sets in software development and the landscape photography aligned, and how this type of a collision turned into a great story of the Northern Lights hunt. So it all started with a very simple question. One day, a friend of mine asked me a question like, which country is the best to visit and witness the Northern Lights? And I was like, probably pick the one you like the most. So technically speaking, pick the one you like the most, or like go to Alaska, go to Svalbard, the north of Norway, goes to Iceland, Norway, Russia, Finland, Canada, Sweden, or Greenland, or even North Scotland. Just if you haven't been to any of these, decide upon your budget. So that's probably the simplest answer to this question. However, the phenomenon from the physics standpoint, the fact of the presence of the Northern Lights in the sky is the coincidence of multiple factors. So the Northern Lights phenomenon is something that can be described as a set of measures, so basically numbers, because it's physics. Although it looks like a magic in the sky, and ancient people thought that the sky is being on fire, but we're living in 21st century. We are all in some sort of scientists, so we can do some measures and apply some math equations to those measures. So I decided to answer this question in very uncommon way. So I asked myself whether I can answer my friend's question in a manner of software engineer, with a certain background of data analysis. So from that moment, the answer to the question, which country to visit, was nothing but the result of math equation. So in here, I decided to do something reckless and pretty fun. So I decided to establish the Northern Lights Awards. Um, so I didn't really want to get into details on how about how and exactly I was able to give the answer to my friend, rather than focus on the key aspects of the technology I decided to use. Um, so in order to just save you time, if you want to read the whole case study description, including some math equations, some rules, and how to build the math around this problem, you can visit the GitHub page, GitHub organization. There's like a single repository where you have the whole description of the experiment and how it was performed. But I need to it would be unfair not to mention, with the help of what I was able to make this case study happen. So I want to give some credits to Dark Sky service that provides. This is one of the like best services on the internet that provides you historical weather forecasts in a matter of REST API, and of course the Potsdam Center of Geoscience. So this is like a huge organization in Germany that collects the geo data through the year and publish them on their GitHub, or oh no, not the GitHub. They have like an FTP server where you can go and download your data sets starting from like um, 1940s, maybe 1950s. I don't recall exactly like what's the earliest data set is, but they do this, and the amount of work they have done, it's incredible, especially if you are you're a physicist and also you trying to get into geoscience, so some science about our Earth and how it uh, inter, how it acts in our like solar system. So it's pretty interesting to learn, especially if you haven't been at any time into this type of a science, because basically it extends your vision to the world, so you get a slightly smarter in terms in a slightly different way rather than just software development. So before I would jump into the description of the technology itself, I want to give some describe some key aspects that are pretty crucial for observing the northern lights. First of all, it's weather. Uh, Basically, in order to see the northern lights clearly, you need to get a clear sky. That's pretty obvious. Maybe just a little portion of clouds, but just it has to. The visibility should be the sky should be clearly clear. The visibility must be beyond like 30 kilometers, which is like useful for human's eye. The other one is the weather, the location. Sorry. So as far as you know, there are like two lights that happening on Earth. So basically, we have a northern lights and southern lights. So the one happening around Arctica, um, around like the Arctic Circle, and the other one happens in Antarctica. So in this case study, I was researching the northern hemisphere. So obviously, I will be talking about the countries that I've mentioned before. So you can see the northern lights on the if you go far north. So like the countries that I've mentioned in Europe and in America, those are like just Alaska state, Canada, Greenland, Iceland, and the European countries like Sweden, Finland, Norway, Svalbard as independent area. So that these are countries that you where you can see the northern lights. And of course, it's all about the seasons. So the northern light in like there's like a polar day and a polar night. So you can see the northern lights only during the polar night. So polar night starts somewhere in autumn, then winter, and a smaller portion of spring. So within these months, like if you're gonna go and read about that, they will say like from September until end of March or very beginning of April. This is the exact time when you can see the northern lights clearly on the northern hemisphere. Um, and so, which technology? So, which technology I choose as the most comfortable one? But let's make it clear. The term comfortable technology to use is kind of tricky here, as it actually declares a set of demands to the technology, and it has to comply 100% rather than just go above the threshold. So let's speak a bit about those requirements. So in this case study, I took only few European countries that are were basically that have stations that collect the data of the related to the northern lights and the sun's activity. So let's let's make it clear, like completely. The technology that must be comfortable to work with the sequences. In my case study, like each country that I've researched is represented by a set of the GPS locations, 9 or like more. Those are locations where people actually reported a clear visibility of the northern lights. So on each country that I've picked, the number of those locations is vary because not all the countries they lie within the same altitudes, so like longitude and latitude. So they're like the least number of GPS location for one country is like 9. So each GPS location is uh, that relates to 8 daily measures that performed by those stations in those countries, and there are like eight. No, sorry. There is like 9 hourly measures during the night hours for each GPS location. So eventually, we're getting at least like 3,000 measures per single location. Now imagine that you have at least 9, so we have like 27, and certain countries have like 16 different locations where people witness the north lights. So the amount of data is pretty growing because it's not just a single string attribute. It's like it's a huge set of data that must be somehow processed. So, and it can actually go beyond like even 100,000 records per country. So just imagine this amount of data that needs to be processed. And all of those data is a sequence. But it's not like a single sequence. It's just a number of data sets connected through the particular points through the GPS location in particular. Um, so the other one requirement is the pipelines. So the data processing pipelines are quite crucial in my case, as the whole problem solving is a set of sequenced perceptrons. So if you've been familiar with data science or have ever read any article, like even introduction, oh sorry, um, the intro ones, the perceptron basically is the way is the way computer imagines how the brain works. So basically, each perceptron is a set of mass manipulations on the data that basically gives the certain output of the income data. So as I said, like the whole problem solving is a sequenced perceptrons that process multiple point connected data sets from the dark sky and the Potsdam University into and the case study is all about combining all these two things into a joint country-based statistics in order to identify like which country is the best to visit. The other thing is parallelism. So the sequence and the pipelines applied to that sequence must be capable to be executed in parallel, because since the case study is like some sort of a yearly challenge, the technology must be capable to run perceptrons in parallel. So like the good thing is that the data is quietly efficiently splittable. So because at most of the times the data points in the data sets is are not dependent, and they can be the perceptrons on that data can be executed in parallel. So technically speaking, each country can have its own um, um, each country can have its own pipeline that must be capable to be executed in parallel to run the perceptrons for each GPS locations. For that GPS location, you need to get the historical weather forecasts. You need to get the data from the Potsdam University, and since we're talking about like three actual seasons, it's autumn, winter, and spring. It's somewhere around like 128 days of the actual dark time on the northern hemisphere on the north, like behind the or beyond the polar circle. So, and the one of things that pretty important is the input-output framework, because both Potsdam University and the Dark Sky, they provide in their data through the API endpoints. So like through the HTTP REST endpoint in particular. So in the context of parallel pipelines, it's very important to reduce the amount of time that being spent awaiting for the response from the remote host and basically give that time of the executor to run another task. So, and ideally, the I/O framework of the technology must be capable to provide async API, because that's basically the way to free up the executor time and basically allow other tasks to be executed while awaiting for the response from the remote host. So, and the last part, I wouldn't say like very important, but still, I wouldn't say like crucial, but really important. The typing system is really important, as there are some data types that require additional parsing steps. Like there has to be like a same API to work with those data types. Um, and also we care like about our mental state, so we don't want to work with technologies that doesn't look good or either uncomfortable. So that's very important as well. So I decided to since I had some background in data analysis, but in the context of Python, I decided to basically do a very short comparison, because like we all know that Python be known as the one of the best tools to do some math, because it has a pretty good C Python implementation of most of the libraries. Um, so I decided to compare some very, very crucial types. So Python has generators, but their API is like very, very awful, because if you haven't seen that, I just Google it and you're gonna understand. So Java has streams type, which is great. Like in the data set that I've processed from the Dark Sky, uh, they provide the date information in RFC 3339, which isn't available in Python, but very simply parsable in Java. And also built-in HTTP client, which is a blessing in Java, and also it has its own great features that I have used in this particular case study. So, and the winning technology is, of course, yeah, Java. So just Java for data science. Don't say you're unsurprised, like, aren't you? So there are like multiple why questions why, and I'm gonna list out some of them that I found pretty crucial for this particular case study or task name whatever you like it. So Streams API. One of the greatest thing that happened to Java Collections framework was the introduction of Streams API. Uh, a stream doesn't store the collection itself, but it just represents the pipeline of the processors that applied for each item of the particular collection. So for all data points, all I had to do is to define a set of perceptrons, and they're gonna process the whole collection without storing any bits of data that would be processed. And of course, like if you're familiar with the Streams API, by the end of the execution of each perceptron, you need to do a collect. You need to run a collector against the stream in order to get one of those uh, types that will represent a stored version of your the result of your perceptrons. So basically, if you have multiple collections, you can basically collapse them into a list, set, or whatever, which is iterable. So one of the very important things that you may find in the what that was very important for this particular case study is the parallel execution. As I noticed, as I mentioned before, so as long as my data is efficiently splittable, there is no point in running them in a single thread. So I want to speed up the execution. I want to speed up the HTTP routing. I just want to get the result faster. So if you're going to take a look at Python, for instance, Python really suffers from global interpreter lock. So you can actually scale out the execution itself, because if the execution itself is a CPU intensive task, there's no way that Python will be able to run that in parallel, because there's only one thread running at one time. So you can split your data efficiently, only running multiple interpreters. So it's not very efficient and very not programmable way for this type of a case studies. In the meantime, Java can run multiple threads at any time, especially if and the number of those threads efficiently depends on the number of available CPUs on your machine, your server, or wherever you run your code or a container. So as you know, the Streams API also have like a small attribute that named as is parallel. So you can turn each stream into a parallel one. So if you ever wondering how the parallel streams work, so when you execute the stream in parallel, there is like a global the global executor in the runtime that that the stream will reuse in order to distribute the amount of items to process on each thread that will run on the dedicated CPU, which is definitely not possible in Python. So, and technically, you can say to the JVM that the default executor, sorry, not global, the default executor can actually run more threads, even more than you have CPUs, because by default, the number of threads in default executor is lower on one from your the number of your CPUs. So you can make your stream process your collection more efficiently with more threads. However, there is a pretty great formula that was proposed by Doug Lee, who is the he works from one of the universities in New York. He's very familiar because of his books related to parallel data structures. So he in one of his articles related to parallel streams in Java, he proposed this particular formula. So the S stands for the stream that was derived from your collections. The parallel stream basically said that this particular stream will run in parallel, and the uppercase F stands for the operation that will be applied to this particular stream, or in terms of data analysis, F is a perceptron. So in order to identify whether it's efficient or not efficient to run your collection in parallel, is to to do some calculations. So you need to know the amount of the size of your collection you need to process with the through the stream, and you need to understand the cost of your operation that you will apply um, to each item of the collection through the stream. So imagine, like, if you want to just run a very simple operation, like you have an array of like numbers, and you want to increment each one. So the like +1 operation on the integer, or whatever that would be, is pretty cheap. So it means that in order to make your processing efficient in the context of parallel streams, is to make sure that your incoming collection is big enough, because it may appear that the overhead of the provisioning of more threads to process your parallel stream will be inefficient comparing to the cost of the operation. So basically, the amount of time that the runtime will spend to create more threads will be lower than the processing of the whole collection. So, and it's always important to keep this in mind when you work with a parallel stream. And here's our like a few quotes from Doug. So uh, if it takes longer to partition your data than to process it, then it's not so you need to run your collection, you need to run your stream and processors within it in a sequential mode, because as I mentioned before, like if your data set, if the processing function for each element of your data of your collection or data set takes less time than the provisioning the whole infrastructure for the execution, it's not very efficient. It will basically consume the time of your execution, but we are here to basically make your code run faster. And also, the data structures tend to be efficiently splittable if they internally supports random access. So some of the data types are not very efficiently splittable, and the amount of time that the runtime will spend in order to reduce your collection onto the items will basically be inefficient and may consume additional time that we would like to avoid. So probably the most splittable type is the array list, as far as I can remember from his article. But you can find his article pretty easily. Just basically Googling Doug Lee parallel streams. It's pretty easy to find. So, and I'm really sure that when the project Loom will be delivered within the OpenGDK, the efficiency of the parallel stream will increase in our apps, because the project Loom will deliver a very important feature, which is called the virtual threads. So as far as for now, like when you create a Java thread, it basically maps to operation system thread. But with Loom, there will be a capability to basically rely on carrier threads. So basically, the runtime will create only a certain amount of those carrier threads, but the other ones that defines within your application will be virtual and not would be mapped directly to the operation system thread, but they will be executed on the carrier threads. The greatest thing about that is that if you have an IO operation within your virtual thread, the runtime will automatically stop your execution when the IO operation happens, and basically give the time for another thread to keep its execution And then when the another IO operation will appear or the particular thread will end its execution, it will switch back to the particular to the previous task. So it's very important because even for now, the parallel streams are very efficient for uh, for the data analysis because they already allow you to run uh, your uh, your basically perceptrons on your data sets independently in parallel, and you basically will get even more performance boost in time if you will run your apps like on a server with lots of CPUs. It definitely will you will see the performance boost. Although if the processing time and the cost for the each element of your stream collection and derived stream is lower than the overhead for the creating the infrastructure, it would be very inefficient, and you probably will see the time regression for probably, let's say, like the performance regression because your data set is not efficiently splittable. The other part, as I mentioned, the memory efficiency is very important. So for my case study, just imagine that I have like thousands, like tens of thousands of data points. And all I have to do is basically load like multiple collections and then define a stream with lots of perceptrons that will process my data, and they will store only metadata of the pipeline, but not any bits of the collection that it's this particular stream was derived from. Isn't that really great? So before that, it wasn't that very great to work with huge collection, but with Streams API, the whole new world is open for data analysis, the data scientists. They would be they are able to build the pipelines with the current version, like with the latest version of Java. And it's really great because Java is gaining lots of interest in data science. And if you probably noticed that there's a new technology that's been released not so long ago. It's called Trivio. This is one of the Oracle's initiatives. This is like pure Java data science framework that is capable to work with almost any existing types of the machine learning models, and also it's capable to run some data analysis, data science as well. So in the other part, side of the memory efficiency, is the comfortable API. Just imagine how it's great to take a technology that by default has one of the greatest APIs that allow you to define the great pipelines, and just see, and they are very easily debuggable. Even like in the IntelliJ, the JetBrains product, the IntelliJ, they even develop a plugin that allows you to visualize the process of your parallel streams. It's really great, and people start using more and more native Java technologies, stepping away from other tools because uh, as Alina mentioned on the other talk on the Graal VM, so you even can turn your application into native executives. You can do with Java a lots of things that you weren't capable to do, let's say like 5 to 8 years ago. And the Java evolves itself, and it provides more and more great functionality that we really care about as developers, because that's what we want. That's really what we want to, and that's what OpenJDK developers providing us with each new release each 6 months. So in this month, the new thing was released within the JDK 15 is the new garbage collector. So if you've been using lots of data processing in Java, I definitely recommend you to check the ZGC project, and you're gonna see that they were able to nail down the pauses on the JC up to 1 millisecond. Just imagine how many of existing GCs are capable of so. So, and if we're gonna go back to like a small, tiny comparison to Python, you're gonna see that the generators API is very poor and almost unusable for any great development because of its API, and it's basically forces you to fall back to functional programming and hardly usable and definitely hard to debug. Uh, on the other note, the Streams API dictates the code structure, which is great, and also Java is well known for code readability and Streams following the same paradigm. So if you're gonna take a look at any other stream processing, you will notice how easy it is to read the code within the processors. So definitely great. So basically, uh, aside of the dedicated type, every type from the collections has its own method to create a stream. Sorry, and also there's a very simple way to define those pipelines, and it's very important for any collection processing and data analysis, especially if your data is efficiently splittable. And streams are usable. So let's take a look at very small example that includes they basically address the function interface. So here's like a very simple task. So basically take a list, do some stuff, and then just collect to um, so basically that's what it is. But still, the whole idea of the stream isn't that once off. So basically you can define a stream and then reuse it and then keep it unclosed and then reuse that one more time. Also, going back to HTTP client, even if you go to like Python docs, you will see that Python dev says that there is no good HTTP client in Python standard library. On the other side, Java has a pretty great HTTP client that already supports every modern standards, including HTTP 1.1, HTTP 2, and also it has an asynchronous API that works through Future, which is definitely great because you no longer need any like Apache Commons HTTP client or Oak HTTP, which involves Kotlin in your development, which is not really great and not really great thing to work with, especially if you're building the modular application through the project Jigsaw. So as I said, Java is great for multiple threads. Java is great for data processing pipelines whenever they include the IO operations or CPU-bound intensive operations. And probably if you haven't checked the case study itself, and and the result of this case study is that in 2019, the best country to visit for Northern Lights was Finland. The second place goes to Iceland, the third to Norway, and the fourth to Sweden. So all of these results were collected by pure Java code involving parallel executions, collections, and built-in HTTP client. And it's way more efficient because all you have is only a native Java code that can be easily compiled through GraalVM into executable, or can be linked through the JLink into executable and basically reduce the size of your runtime, which is very important, especially if you run your application on a containers. That's probably it. Thank you for listening. Thank you for letting me speak. It's time for questions.
Excellent. Thank you so much, Denny. Well, so far there are no questions. Um, yeah, I don't know if into the chat is someone having some question regarding this talk.
It seems there are no questions, but
I
just want to say thank you because seeing the Northern Lights, in my personal bucket list, and I'm sure it's in the bucket list of many people here. So it was like an interesting insight on
Yeah,
again, it's
so
just
the world will get back to normal, just spend your time and travel up north or far south to witness the lights. And it's beautiful for sure.
yes, thank you.
That was pretty cool. Okay, Dennis, I don't know if you could see, but we are doing like
A beer mug.
yeah, remote, and we would like to give this as a gift to the folks that are listen to your talk. So I will ping you into Slack in order to send me a question to post it into our Twitter, and
Mm,
the question will be related, obviously, with your talk. So the winner in Guadalajara will be the one that could get this one beer. Wow.
okay.
Yeah, thank you to our sponsors for that. I don't know if you would like to close with something or.
No, I guess that's fine. I'm gonna just disconnect. Thank you guys for letting me speak in. I hope you find this talk interesting, even though it not includes only like a very technical stuff, but something fun to listen and maybe yeah, just interesting.
Yeah. Thank you so much,
Yeah,
Dennis, again, and good
thanks.
night. Good night to you.